Andrea Ferrari. Here it goes. We'll be talking about machine learning dualities in statistical physics. So how to use machine learning to look for dualities. Thanks.
It's been a pleasure to be here over the past couple of months. And although it feels a bit odd to talk about machine learning after 2 months of discussions about QFT and mathematics, I am very glad to participate in an event which I believe is very important. As Andy said, AI and machine learning is here to stay. And I think we are reaching a point where application in our field are also going to be very substantial. So my goal today is not to tell all of you that you will become irrelevant in 5 years. This will be the other talks, I think. But my goal is a little more modest. I just want to say that machine learning techniques may be used in statistical physics or maybe quantum field theory to study dualities and defects, and to present some results of some explorations I've started to do last year, which I believe have turned out to be quite useful. So this is based on an ICML 25 paper with Pratik Gupta. He's a machine learning engineer who was at DeepMind at the Max Planck Institute in Berlin, and Nabil Iqbal, whom many of you should know. ICML is the main machine learning conference of the year. So just to give some background, this is the link to the ICML 25 paper. In case you are interested in seeing it, what I'm going to talk to you today about is also based on an archive preprint that appeared last year. Yeah, and you can find these slides on my website in case you're interested. So, as a motivation, we all know, at least this audience knows, what duality is. It's a key idea in modern theoretical physics. If we want to define it in broad and rough terms, the same physical system may have 2 or more surprisingly different descriptions. So this is an idea that has been driving what we've been doing for many decades now. I put here an embarrassingly biased set of examples, but starting from bosonization, Saint-Gobain theory, particle vortex duality in relation to 3D mirror symmetry, and so on and so forth. ADS-CFT, of course. Today I'm going to focus on dualities, elementary examples of dualities in statistical physics, which are related to what people have been discussing over the past few months, which is this 2D Ising model, the duality present in the 2D Ising model, which is Kramer-Vanier. So, in a duality, different descriptions or frames are often related at different regimes. They're usually strong coupling, weak coupling, high temperature, low temperature. This is why they are surprising. In all cases, we have a dictionary between observable quantities in the 2 frames. So in a slogan, whatever can in principle be computed in one frame may be computed in the other. But this strong-weak relation implies that computational efficiency may be different in the 2 frames. If you want an algorithm analysis and you want to embrace something like an extended Church-Turing Deutsch thesis, like physical theories are computable, then frames can be thought of as algorithms that, starting from initial conditions or inputs, output some observable things. And dualities are algorithms taking different inputs but producing the same output. So can we make this precise in some setting? So we can try to do so in statistical physics. And to this end, I'd like to discuss a proto-task. So one task that one might have in statistical physics is that given a distribution of states that you may observe, you may want to guess an energy function or a Hamiltonian which determines Boltzmann weights such that what you observe is very close to the predicted probability distribution. All right, so you may have, in examples that we're going to see later, many configurations of spins on a lattice. You will want to ask yourself which energy function is telling me that it is going to faithfully reproduce this distribution. So some machines can perform some of these tasks very well and quite fast. In fact, it was a central topic in machine learning for quite some time. If you know or have ever heard about Boltzmann machines or energy-based models, this is a little bit like this proto-task I mentioned before is a little bit like training what is called a fully visible Boltzmann machine. So for instance, you have an energy function that, let's say, that depends on some variables, the two variables, value plus minus 1, and you have an energy function that looks like this. This proto-task, as I called it, corresponds to find weights in this energy function so that the negative log likelihood of the observed configuration is minimized. So if you want to maximize probability, you may want to minimize negative log probability. And if you want to do that, one simple thing that you can do is compute the gradients with respect to these weights. If you compute the gradients with respect to these weights, you will get expectation values of as computed by the data of these spins of these SS correlators. Later they're going to be spins, and the one computed from the Hamiltonian. So if you want to go to a minimum of this, you may want to use these gradients, but computing them is usually quite expensive, depending on the size of the system and so on and so forth, of course. But one of the issues is that you have this partition function z, which is in general very expensive to compute. So what people have done to circumvent this problem is, or one possible strategy is to try to run some Markov chain Monte Carlo simulations that approximate the expectation values of H, instead of computing it directly. So you try to perform some Monte Carlo estimations, and then you estimate this gradient and try to see where you get. And in fact, if you had worked on some of these problems 40 years ago, you might have won a Nobel Prize in physics last year. Because, I mean, one of the reasons behind the award of the Nobel Prize to Hinton was developing a set of tools that were very efficient to train Boltzmann machines. This is a simple example of this, but it has had a huge impact in machine learning. And so it's, yeah, it's a problem worth considering. So a special case of what I said before is the 2D Ising model or Ising model on a square lattice. So before, I was labeling these spins by some set L. Here we take L to be, or we represent this L to be a square lattice. So each side labels an I. And my weights are only non-zero for SIs and SJs that are neighboring in this case. There are other choices to be made. But this gives you the simplest 2D Ising model with this Hamiltonian here, where you sum over all neighboring spins. Yeah, and this is simply your energy function. So the proto-task I said before was given a configurations, in this case of spins on a lattice, try to learn the beta parameter that faithfully reproduces, that best fits the distribution. In this context, the problem is sometimes, applied to the Ising model, is called the inverse Ising problem. There is a huge literature. These three people wrote a review about it, if you're interested. We'll not use this today until the very end. But at this point, I just want to say that there are very efficient algorithms to simply fit the couplings of Hamiltonian of an Ising problem, so that my previous task is completed. Are there any questions so far? All clear?
So when you said parameters, just the beta, right?
Yeah, in this case, just the beta.
And the lattice is infinite.
Yeah, in principle, yes. You want to work on infinite lattices. In principle, when you need to compute, you take the lattice to be reasonably larger with respect to the coupling. But you want to work in the thermodynamic limit, very large lattices. All right. So today, we will be concerned with a slightly different, but more general problem. So consider a more sophisticated statistical physicist who wants to be a little bit more agnostic about things. You may want to be agnostic about parameterizing or the parameterization of the underlying configuration of states, spins of a lattice, which lattice. You may want to be agnostic about the precise form of the Hamiltonian or energy function, or even what you are observing. So why would you like to do something like this? Well, the guiding principle is something like, the less you assume about what you're seeing, the more a potential description may be surprising or useful. And of course, still, one needs to find well-defined training tasks that are a little bit more relaxed. And yeah, last year I told myself, together with Nabil and Pratik, that it may be curious and interesting to study dualities in statistical physics, precisely because they give you surprisingly different descriptions of the state system. So I think most of you are familiar with Kremer-Savanier duality to the Ising model, but yeah, so let's consider this elementary example of a duality. So we have these spins on a lattice that I assume to be square in this case. The model has a Z2 symmetry. It sends psi to minus psi. The energy is lowest when most spins are aligned. And this duality, Kremer-Savanier duality, is, in this case, a self-duality relating beta at different regimes. So physically, this duality is related to gauging the Z2 symmetry. But I am not really interested in rederiving the duality in some mathematically rigorous way. I am interested in trying to learn it based on data. So, more in details, this is a self-duality which relates the Hamiltonians at different temperatures. The dual Hamiltonian is defined on the dual lattice in general. In the case of the square lattice, the dual lattice is also a square lattice that you may think of in very pedestrian terms as having, just in this case, as having an edge in each facet, and for each link, in the original one, I have a dual link that you can think of as crossing it. It's just a bookkeeping device. What is surprising or unexpected of the duality is that the two inverse temperatures are related. This beta, which act as inverse temperatures, are related in a way so that when one is large, the other one is small. And you can show directly by direct calculations like expansion that the two partition functions of the model at different temperatures agree up to an overall constant. So this is a self-duality of this to the Ising model. So, as I said, this is a large temperature low temperature duality. So if I represent my spins like this, it maps a phase that is ordered, where most spins are aligned, to a phase that is disordered, where anything can happen. And there is a critical point that has been derived based on this duality, actually, which is that beta equals 0.44. Importantly, the map between spin configurations is not one-to-one. It's not that for each spin configuration in one frame, you can find a unique spin configuration in another frame. But still, as I said before, if you have a duality, you expect to be able to compute, to be able to reproduce everything you can compute on one side with a calculation on the other side. So how does this work in this case? Well, one simple thing that you can see is that if you compute a neighboring spin-spin correlator in one frame, it's going to be mapped to a correlator in the other frame where it's also a function of these spin-spins, but with this exponential factor. And in fact, you can verify very easily. You can verify this very easily on a laptop by running some Monte Carlo simulation on a small lattice. You try to compute these two things, and they basically agree. So the question you can ask is, can this matching of data be used to learn the duality? So can this fact, the fact that we can compute certain spin-spin correlates, certain observables in one frame or the other, or that there is a map between observables, be used to learn this duality? Any questions? Yes.
So do we know what? I mean, we certainly know, but I don't. So what are the observables on the dual side? I mean the element. On the operators.
Yeah, so it's what I wrote here. So this is one result of the duality. A spin-spin correlator on one side, you can compute as this e to the minus 2 beta spin-spin correlate x.
Yeah, but so if you want the operators on the other side are still spins.
It's still a function of a link of spin. But in general, in a duality you may have something that is even local on one side, non-local on the other. But in this case, in this simple self-duality, this is what happens. It's known, and I'm just saying, you have an observable on one side, you want to find a map to an observable on the other side that computes the same thing.
Excuse me, could I?
Yeah.
Sorry, I came in very late, so this is
Right.
a very bad question.
No.
Is the idea that you give, it's supposed to deduce correlations on the other side from correlations on one side? Is that what the learning means?
So, yeah. So the frame of the problem is usually you there are algorithms out there that, based on some correlation of spins, learns back where they came from.
Okay.
And now we want to try to apply this to a duality by being agnostic about the form or what it came from. The idea is you start from some correlations of spin, and I will mention this later again, but you'll try to learn back where it came from and you find two solutions. You will understand over the next couple of slides. So, the idea to produce an algorithmic learning of duality is start from some system like this Ising to the Ising model at a given temperature. Then run some Markov chain Monte Carlo simulation to produce a collection of spins, spin configurations on the lattices that is distributed according to this Hamiltonian. If you don't know what these Markov chain Monte Carlo methods are, don't worry too much. It's just you start from a random configuration and you do updates that are guaranteed, random updates that are guaranteed in the long run to approximate the distribution that you like. It's a little bit the idea. But then, once you have this large collection of spins, what you can do is you can compute any observable that you like based on the spins. And this is going to give you estimates for your correlators in one frame. And then if you want to kind of learn the duality, you can upgrade the task I mentioned before as follows. Suppose that you have some lattice with some spins, as well as a reasonably general Hamiltonian. You parameterize some general Hamiltonian with some properties that you may like. A sufficiently local observable, like an observable that depends on sites on a specific site on this lattice and gives you a number. You can parameterize it as you like. The more general you are, the more likely it is that you will find something new or interesting.
What do you mean by some lattice? How general?
Yeah, in principle, it's a choice. It's an arbitrary choice you can make. You can try to match things. In this case, we are going to take the lattice to be again the square lattice because we want to rederive the Kramers-Vanier duality. But in principle, as a learning task, you want to be as agnostic as possible about what you have in front.
For example, the dimension is the dimension, for example.
Yeah, I mean, that you may want to take to be fixed, yes. And then, so you parameterize some observable, and you want that the correlators of these sufficiently general observables match the correlators that you computed from your original model using Markov chain Monte Carlo. So the above strategy may be thought of as a decoding and encoding process. You start from a Hamiltonian, and you generate a large collection of lattices. You compute some observables. You know their expectation values. And you want to learn back some Hamiltonian defined on some lattice together with some observable that reproduce this all of these correlators. Any other questions? Is the strategy clear?
How do you avoid that it gets stuck on the original?
That's a possibility, and it will happen. But in general, you want to minimize these functions, these distances in correlation functions. If there is no duality, then there is only one solution. If there is a duality, there are more solutions. Yes.
How do you deal with boundary conditions?
Boundary conditions?
Yeah, all these duality transformations are to really have a one-to-one mapping. You need to change the boundary conditions.
Yeah.
And basically, to do this, you have to understand the duality anyway. So I don't understand really how you would.
Right. Well, we work on. I mean, on very large lattices, like almost infinite for practical purposes. And there, at least, we didn't really see issues. We can talk about this in a few slides.
But so you're only considering cases then where the correlation length is very small.
Yeah, I think so. Yeah.
Because obviously, once you get close to
if you get, I will mention some of these things. If you get close to the boundary, if the correlation length becomes fairly large with respect to the size of the lattice, then things in the duality start to diverge. But so computationally, you need to work with couplings that are small with respect to the lattice you're working on. So provided the problem is set up correctly, as I was saying before, you should find roughly two solutions. One is the original model, which is the original lattice, the original Hamiltonian, and the observable you estimated before. And if there is a duality, you should find a dual solution, which is the dual lattice, a Hamiltonian and a dual couplings, and the dual observable.
There could be more.
There could be more, yeah. But at least when you know that one is there, you can have at least two. So to achieve this result, one needs to identify a suitable parameterization of the Hamiltonian. One needs to parameterize a suitable observable, define an appropriate loss functions that tells you when correlators match, and then develop an optimization schemes for getting to optimal parameters where these things are supposed to match. And this is a little bit the goal of what I want to say. So, just the first exercise that we did was, so suppose that your lattice is also a square. In principle, you can parameterize your observable as any neural network with a large input of spins, and one output, the value of the observable. But also based on the remarks of Frank before, you can assume that you want to find dualities that are reasonably local, one with respect to the other. And so you parameterize the observable as taking as input only a neighborhood of the spin-spin correlator you start from, and which outputs a number. And we did this by using some parameterizations that are called Gumbel softmax. We introduced 3 free parameters. So it's just a function that takes out of one spin that labeled by a spin that takes neighboring spins as input, outputs a number, and this Gumbel softmax is interesting because it's done in such a way that you can control how spread out, not control, but you can assess very easily how spread out the observable is, how much each of the links contributes. But in principle, it's just we assume that we have a reasonably local observable. So inputs on a neighborhood of spins, outputs a number. Right. So, and then recall that the desired matches is that the correlators of these observables all agree with what we computed before using Markov chain Monte Carlo. Standard approaches in order to do this in machine learning involve kernel methods. So what's the issue here? The issue is that you want to match OIJ to something on the other side, but also the product of OIJ, OKL. And these are a little bit like you want to match all moments of a statistical distribution. And usually when people need to treat these problems, they find functions that contain in their expansion all of these sort of moments, and so that they go to zero if and only if all of these moments agree. So we tried that, but some care is needed in this case, because you have problems when Si and Sj are the same. On one side, you always get one. Correlation functions involving faraway spins, if the couplings are small compared to the size of the lattice, will carry little information. But when you run this Monte Carlo simulation, noise accumulates. And so you get a noise to signal problem. So the solution is just to focus on a handful of these correlators that contain already sufficient information. So more formally, for any function labeled by a link, if you take A to be a subset of the links, you can define the product of the function values over the links. And our loss function will be the square difference between the expectation values of correlators of these products computed in the original frame using Markov chain Monte Carlo and the dual frame for some collection of links. Are there any questions? Okay, so is this reasonably clear? All right.
You want to minimize L, right?
Yes.
And minimizing means that you have the theory, you approach the duality.
Yes. If you minimize L, you will approach the duality. I mean, you. This is a choice yes?
I could pick any random thing I want.
Yeah.
Six-dimensional supersymmetric theory.
Right.
And I could plug that in and I could minimize these things and I'll get some numbers.
I mean,
duality would be where it's really, you minimize and you get zero.
Yeah, yeah, that's right. That's right. So the idea is to formalize the. If you look at any duality paper in physics, you start from two things: you compute observables, and then you see that they match. And the idea is to formalize this thing in a setup where you can control it. So in this case, the output of the computation is you want a map between observables, and you want that the correlators of these observables match across the duality. So when you minimize this function, you should get something that is like a duality. So in the case at hand, here is a collection of links across which you want to match this duality. This is, we call them features in our paper, but these are large enough or reasonably. I mean, if you can already match these observables as distributed across the lattice like this, already quite good. In principle, you want all possible products of things to match, but then you can select a subset and then check that they match more broadly. But for the training, it's one delicate thing is to select an appropriate subset. All right. So to minimize the loss, not compute, we need to compute gradients with respect to the parameters that we have that we're used to model this thing. So some parameters are the couplings of the Hamiltonian. Other parameters are the parameters that parameterize our observables. Now, the gradients with respect to the parameters in the observable, from a computational point of view, are very easy. You can use what is called backpropagation. It's a standard method to compute gradients of loss functions in neural networks based on clever use of the chain rule, essentially. But you can find it in standard packages. You don't need to do any more than writing loss.backward in some code. Computing gradients with respect to the couplings is harder, as the coupling basically directly affects the probability measure of the sampling. As far as I can tell, classic methods to efficiently compute gradients with respect to these couplings, in this case, like in the inverse Ising model or methods like contrastive divergence, cannot really be used. However, a simple computation shows that gradients with respect to the couplings can be expressed in terms of expectation values with respect to the dual Hamiltonian. So this means that you can estimate the gradients themselves using MCMC. This goes back to what I told you at the beginning. But so the idea is you compute the gradient with respect to the Hamiltonian with respect to the couplings, or the loss function with respect to the couplings in the Hamiltonian. You realize it's an expectation value. Therefore, you can approximate using MCMC, Markov chain Monte Carlo. Okay, and so we can run this optimization problem on a fairly small lattice, but let's say 8 times 8 at different temperatures. To start with, it's already interesting to see what happens when you start with the Hamiltonian truncated to the Ising Hamiltonian. So you have only one coupling, which is what I was calling beta. And implementing this optimization scheme I mentioned before, it's already quite remarkable that you can reconstruct the theoretical, you can basically reconstruct the theoretical result. So these are the temperatures that the machine finds that optimize this problem.
The dots, right?
Yes. And you can run as many runs as you want, varying your original temperature. And this is...
There are two different types of crosses. There are some thick ones and some thin ones, right?
Sorry, what do you mean?
I see.
No, just...
just the crosses, right? Nothing.
Yeah. It's just... yes, just focus on this big blue crosses. And as you vary the original Hamiltonian, you will find solutions at various runs. Some will be the original temperature, some will be the dual temperature, and some land on the antiferromagnetic image of the original model. So it also learns that there is an antiferromagnetic image. And if you run this many times, you can get enough data to reconstruct the theoretical result, to fit this curve and reconstruct the theoretical result.
Is there the region of betas you chose? Is there a reason for that, or?
Once you pass the critical point, it becomes hard to train for reasons that are quite deep.
At beta equals
0.44. So that's why we only display for the original model things.
errors start appearing, right?
Yeah. It's more than errors start appearing is that the process of computing these gradients using MCMC becomes quite unstable. So we can compute things very reliably in one phase, but as you can see in the dual, we discover the other phase.
Is that where the cross, right? The two lines cross.
Yeah, so this is the dual, and yeah, so the dual frame, and so it's quite nice. I mean, you just start by parameterizing some reasonably general local observable. You parameterize. I mean, you take this Hamiltonian, and you run an optimization scheme, and you precisely land on on the solutions that you wanted to land on. So even if you didn't know about this, you could have, learned something from it. So we can have a look, or a more detailed look at the training dynamics. So here, well, we can see that there are some runs. One is, here are runs are displayed where at some temperature, the recovered frame is the dual frame or the original at different temperatures, just for comparison. And we can see that, a few things. First of all, the loss goes to zero very quickly. The optimization works very well. The temperatures that we saw in the previous graphs approach very fast the expected original and dual temperature. The mapping of observables is also quite interesting. So as I told you before, this local spin-spin correlator in one frame is mapped to this exponential-like correlator in the other frame. And this pane C here tells you precisely that once the dual model is found, the value of the observable that we have parameterized lands precisely spot on the expected dual value. So you don't only learn the relation between the temperatures, you also learn the mapping between the duality, the mapping between observables very reliably. And so, okay, we have found, we have rediscovered Kramers-Vanier, defining a slightly more general optimization problem that people are used to, that has two solutions. There is an interesting subtlety, which is really, although I have a square lattice on both sides, I told you before that the dual model lives on the dual lattice. And things are a bit different on the original and dual lattice. In particular, if you think about this image here that I wrote, this heuristic but useful image, if you have a square in one lattice of products of spin is mapped to a cross in the other one, right? And you can actually see this feature in how we parameterize the observable. I told you that, so we picked the observable to be sufficiently general as a neighborhood of spins. And if you look at which, and what you can see is that this observable is always picking one link. When you optimize this thing, and moreover, the link in the neighborhood that is picked is in such a way that this relation between the original model and the dual model, the original lattice and the dual lattice is reproduced. So in other words, the information that the model lives in the dual lattice has been hidden into the form of the observable. This is just, in principle, there would be other ways to do this. And you can look at the frequency with which links are selected, and they correlate perfectly with whether the model lands on the original model or on the dual model. So in some ways, the system has learned that the dual model lives on the dual lattice. Okay, then some details and problems. So computing gradients takes time. These Markov chain Monte Carlo chains need to be equilibrated all the time. It's quite expensive. These gradients are also noisy, so one should use some variance reduction techniques to control this sort of noise. The training, as I was pointing out before, rarely converges when the original model is in the ordered phase. And this is similar to observations that people made in the context of the inverse Ising problem. It's probably quite deep. For scarcity of computational resources, we worked on very small lattices, but still it took on laptops and so on and so forth a long time to do the runs. You just ask it to do them once you go to sleep, essentially.
So you did it on a laptop, or?
Most of the things, yes. Then when we had to serialize things, we used some clusters, but you can, individual runs you can run on laptops in a few hours. And adding more couplings, of course, complicates things. So in any case, given the success we've had with Kramers-Vanier in the standard to the Ising model, one can consider generalizations, like what happens when you apply this framework to more general models. There are obvious candidates to look at, like one is next to nearest neighbor, one the plaquette model. The next to nearest neighbor to the Ising model has interesting dualities to brick wall or honeycomb lattices. This is because if you have next to nearest neighbor interactions, the lattice is basically a triangular lattice, and so the dual is hexagonal, like a brick wall. I am not aware of detailed studies of the duality, explicit study of the duality in the plaquette model. Maybe people know, but I'm not an expert, but as far as I know, I haven't seen much data. In any case, it's interesting to ask what this model does if you introduce plaquette terms, for instance. And if you run this on the plaquette term, for the plaquette model, you actually get something quite interesting. So these are the two couplings. So just to be clear, the plaquette model definitely does not have a self-duality. But what we did is we tried to see what the system would do if we forced it to optimize these things on. If you want to kind of deform away from kappa, from the standard duality, and see whether there is some approximate relation between two plaquette models. And what you see is that when kappa is 0, well, you rediscover the original model. There are these square boxes here. It also discovers the duals that are over here. This is the diagram that we saw before, but flattened out. When we let kappa be non-zero, it lands again on the original plaquette model. It doesn't quite find a dual, because of course there is no self-duality to the plaquette model. But the interesting thing is that from the dual points, there are like lines emerging in the kappa beta plane that are anti-diagonal, approximately. And the reason, these are very few with respect to the honest duals that you find. And so you might ask yourself why this happens. And the reason is that if you think about the model, when this plaquette model is deep in the ordered phase and almost most spins are aligned, you can get an excellent approximation of it in terms of rare and isolated spin flips. Like things are mostly aligned, but there are isolated spin flips. If you look at the probability of a single spin flip to happen, it only depends on the sum of beta and kappa. So approximately in that phase, the model it only depends on one parameter. And so the machine learning model learned that the model becomes effectively a one parameter model, and that all of the physics along of most of these anti-diagonal pieces is approximately the same. And if you look at the loss between observables in these phases here, it's also very good. So based on the noise we had was as good as the, relative to the noise we had, it was as good as the original model. So even on a square lattice, one can find approximate duals for these plaquette models deep in the ordered phase. I mean, I hadn't thought about this before, and it was very surprising to see the solutions and to understand where they came from. Now, since we are talking about, okay, just to pause for a second, since this whole program was about defects and boundaries and so on and so forth, I've tried to not to talk about boundaries by working on relatively general lattices, but one thing you may notice is the following. If you are a slightly less clueless physicist, if you want to be slightly less clueless about things and actually try to have some physical input on the duality, you may notice that the spin-spin correlators that we have a topological nature. This is for purely kinematical reasons. So what does that mean? Is that if you take a product of these spin-spin correlators on a chain like this, then since the spin-spins on the internal links are all one, it only depends on the endpoints. So whatever path you take, you should, connecting these 2 points, you should get the same answer. And how does, of course this is, this is a stupid observation in principle, but it tells you that these correlators that we're looking at are topological. And then you may ask yourself, how does Kramers-Vanier implement this topological mapping? And it does not take much in the context of this program to understand that the way in which these topological features is mapped on the other side is by means of the most obvious topological line that you have, is the topological line implementing the Z2 symmetry. So the products of spin-spin correlators should be mapped to the topological line implementing the Z2 symmetry on the dual model. So there are 2 things that you can take away from this. One thing is that, well, if I am slightly less clueless, I realize that for kinematical reasons my correlators are topological. Then I already know what the form of the observable on the other putative side is. It's a topological line. Whatever model you take, you can look at, with a Z2 symmetry, you can look at the topological line implemented at symmetry, and this is what you can try to match. This is one takeaway that you can have from this. The second takeaway is that implicitly, when I relearned the value of the observable before, I learned how my topological lines look like in the dual model. So I believe that an interesting and and doable optimization problem to set up, which is something that I've been discussing with a student here in Cambridge, is well, set up some optimization problems that find topological lines in lattice models. You simply parameterize a reasonably local observable, you enforce invariance under the path, and you train the model and see what observable you get. What we had before is an instance of this. We recovered a chunk of the topological line implementing the Z2 symmetry. So one task that you could have is minimize a suitable loss function to find topological lines. But okay, if you assume that you already found some suitable candidates of topological lines, then the problem of learning good approximations for dual models or honest dual models reduces again to the inverse sizing problem. Because all you need to do is to fit the parameters in the Hamiltonian. So the idea is, if I start from these correlators that I know are purely topological for purely kinematical reasons, I write down a model which has a topological line, so it has a Z2 symmetry, and I try to, I can find, it's easy to find the topological lines, the obvious topological lines that implement the Z2 symmetry on the other side. And then all I need to do is to train these machine learning methods on the couplings in order to match the correlators. And when, in the context of these Ising models, it turns out that it's very efficient to find the best coupling by using consistency conditions that are in the model. Like, I don't want to go into details. Again, there's a huge literature on it, but essentially you may find consistency conditions within the same model that tell you that some correlators are related to correlators with the coupling inside, and then you want to minimize this by using Newton methods, for instance. But so we ran some tests assuming the form of the topological lines in the next to nearest neighborhood model. We perturbed away from the known duality of the Ising model. And again, we found reasonable matches of all correlators. So models that, for all practical purposes, look, there is an effective dual description that for all practical purposes is good enough. And to go back to the question we had before, we optimized this next to nearest neighborhood model for certain values of the couplings. We got some very good candidates for an approximate dual coupling. And then you compute the spin-spin correlators as they, the correlators between spin that are further and further. And you see they match all very well until you reach roughly half of the size of the lattice. And then things start to break down because you have topological effects. You can have, and then you have problems with boundary conditions. But I think I want to conclude here. So the standard problem of fitting parameters in a Hamiltonian of a statistical model energy, of an energy-based model, has interesting generalizations. This is the first takeaway point that I would like to make. It is possible to define duality discovery in statistical physics, at least of some dualities, as an instance of these more general problems. Solutions so far, will lead to the discovery of non-dualities as well, and they also hint towards interesting physics. Again, this is was just a proof of concept, just an idea that we've been trying to develop. There are several future directions that I believe are interesting. One is to study this machine learning problem better. meaning that this idea of learning both parameters in Hamiltonian and observables, which I believe is interesting for physics, has not been developed too well. Then, based on what I said, and in the context of this program, I think even though these models are studied very well, and people know about all sorts of topological defects that exist in there, in principle, it's not hard to set up optimization problems that find topological defects. Of course, as going back to some comments I had before, one would like to generalize duality discovery. The idea that you start from algorithms that produce some inputs based on parameters and you optimize to find dual descriptions is very broad. This is just one context in this which works. More modestly, we can apply our framework to more statistical physics model, and it's more of an engineering problem than anything else, I think. Yeah, and I'm gonna stop here, and I thank you for your attention. Yes.
I'm confused about your packet model. Of course, there's an exact duality. There's an exact dual model.
Yeah.
So it only has to do with symmetries. So your dualities have nothing to do with the actual Hamiltonian. It has to do with the symmetries of that model.
Right.
So you can immediately write down the exact dual one of the packet model. So why did you not find it?
So, but is it a self-dual model? It's not a self-dual model, right?
Of course, it will have different terms, but that's the whole point of dualities. There's no self-dual
Yeah,
models.
yeah, yeah.
Are only, this is basically, there's only one. Basically only one model, or actually you need to have some very simple symmetry to get.
Yeah. No, that's right.
The whole point is that there is a systematic way of.
Yeah. As I said before, it's just because we didn't try to insert the right couplings in the Hamiltonian. We just try to perturb minimally the setup we had with and try to stupidly, willingly, stupidly, for self-duality in the plaquette model and see what happens. But in principle, if you write down the right Hamiltonian with the right terms, you should find it. It's just an assumption that we made just to test our framework further, but that's it. Yeah.
It would have been very natural to do this, of course.
Yeah. No.
Exactly what terms it is.
I simply did not have time to study these examples more broadly.
And then actually the second question about your topological lines.
Yeah.
So of course, for the Ising model, this is very simple. They
Yeah.
are just products. But in general, the topological lines are actually quantum circuits that are entangled.
Yes.
This looks very hard to just
Right.
try any quantum circuit. So how will you set?
Yeah, I don't know. We can discuss this later as well. But I think in principle, you should find some. Yeah. You should find some the broad way of parameterizing things, and once you do that, you should in principle be able to determine the dual lines. But I'd be happy to discuss later about possible strategies. As I said.
I would be very surprised that you can see this topological.
Yeah. We can.
Not knowing basically where you have to go.
Right. In this case with Z2 symmetries for models, it's very easy to see how they look like. To compute the topological lines is very easy, right? You look at some region where you perform the symmetry, and you look at what happens at the boundary. You just look at the Hamiltonian, it's a one-line computation, so it's very easy. But indeed, more generally, I'm saying that I'm just trying, I'm just trying to find optimization problems you can run on a laptop to check the framework, and then in principle, the hope is that one can generalize this broadly. But I'm agnostic about how far you can push this method here. Because, as I said before, from a machine learning viewpoint, the idea of optimizing both the parameters in Hamiltonian and some observable, or something that should represent a topological line, has not been studying much. So we had just to work with what we had.
Yeah, but I think the important thing is that these topological lines are completely independent of the actual Hamiltonian.
Right.
So they are the same whether you do it next nearest neighbor interactions or not. This will not change the topological lines. It's
Right, but they
something
will
around
be.
facilities.
I understand. But even in these stupid examples, finding the topological line is not finding the Miltonian. It's a separate problem. You need to find the
I
observable.
disagree. If you have the topological lines, you now have to do the mapping from the terms in one
Right.
and one to the dual one.
Right.
So
Yeah.
it is the same.
Yeah. Yes.
So the space of observables in these lattice models seems really vast, and the
Yeah.
basic model, it seemed important that you already knew on the dual side sort of class of observables you were after.
So, yeah, in principle, you know, if you have an observable, it's simply a function from the links to the real numbers. So the spin configuration to the real numbers. And of course, it's functions like this have many parameters, even if the spins are plus minus 1 valued. And so if you want to find something, we simply, you know, you can make assumptions that are quite restrictive, like the observables are reasonably local. This was our main assumption, so that we reduced the number of parameters we had to tune. But it's true that it's a matter that the broader you want to be, the more parameters you're going to have in the model. But that's about it. Then it becomes very hard to train, and you need lots of data as well. But in principle, as I said before, as an observable, you can take an observable that is has broader range as you wish.
I mean, you have this exponential function of the spins on the lattice and the dual.
Right.
Even if it's still local, it seems like there's a vast function space of.
Oh, but it only inputs two numbers. It's plus minus 1.
I see.
So it just turns out that as a function of beta, it's this exponential function, but that you don't care about, because you tune beta and you find what number it is at each point, right?
I see.
Yes. So it's not that you have to search for a large space of functions in this case. You just need to assume that it's a reasonably general function that inputs as an inputs that 2 to the n squared and outputs something. But you don't have to look in the space of function for something very general. Yeah.
Yeah, well, we should end there. Let's thank Andrea again.